Welcome to Talk 7. Today's topic is one of the most practically relevant in all of clinical veterinary medicine, diagnostic test accuracy. Every time you run a point of care test, order an ultrasound, or evaluate a new biomarker, you are implicitly relying on the concepts we're going to cover today: sensitivity, specificity, predictive values, ROC curves, and likelihood ratios. The good news is that once you understand the 2x2 table, everything else flows from it. The critical insight, and the one most clinicians miss, is that a test performance in a published study may not reflect its performance in your practice because your patient population has a different disease prevalence. We'll unpack exactly why that matters. Let's get started. Here's our roadmap. We'll build from the ground up, starting with the 2x2 table, then working through each metric in turn. The key theme throughout is that no test metric exists in isolation. They all depend on each other and on the clinical context, especially disease prevalence. By the end, you'll have a practical framework for evaluating any diagnostic test paper you encounter. Everything in diagnostic test accuracy flows from this table. Let's make sure we're solid on the 4 cells before we move on. True positives and true negatives are correct results. False positives are false alarms. The test fires when there's nothing there. False negatives are missed cases. The test fails to detect real disease. In the example on the right, 95 dogs truly have the disease. The test correctly identifies 85 of them. Those are true positives. It misses 10 false negatives. Of 205 dogs without disease, the test correctly clears 190 true negatives and incorrectly flags 15 false positives. Now we can calculate every metric we need from these 4 numbers. Sensitivity and specificity are the 2 fundamental test characteristics, and they describe the test itself, not the population. The mnemonic SNOUT, a test with high sensitivity when negative, rules out disease. If sensitivity is 98%, a negative result means there's only a 2% chance you missed a case. Use high sensitivity tests when missing a diagnosis is dangerous, like ruling out pulmonary thromboembolism. SPIN, a test with high specificity when positive, rules in disease. If specificity is 99%, a positive result is almost certainly a true positive. Use high specificity tests when a false positive would cause harm, like before committing to chemotherapy. The trade-off: you can't maximize both simultaneously. Lowering the cut point increases sensitivity but decreases specificity. This is the fundamental tension in diagnostic test design, and it's what the ROC curve visualizes. The concept that trips up the most clinicians, and it's critically important. Predictive values are what you actually use at the bedside. My patient tested positive. What's the probability they really have the disease? But positive predictive value and negative predictive value are not fixed properties of the test. They depend on how common the disease is in the population you're testing. Look at the graph on the right. The same test, sensitivity 89%, specificity 93%, has a PPV of about 40% in a population where disease prevalence is 5%, but a PPV of over 85% when prevalence is 30%. This is why a test validated in a referral hospital population where disease prevalence is high may perform very differently in a general practice setting where the same disease is rare. The sensitivity and specificity are the same, the PPV is not. Always ask, what was the disease prevalence in the study, and how does that compare to my patient population? C curve is the tool for comparing two tests head-to-head and for choosing the best cut point for a continuous test. The curve plots sensitivity on the y-axis against 1 minus specificity on the x-axis at every possible threshold. A test that perfectly discriminates disease from health would hug the top left corner, 100% sensitivity and 100% specificity simultaneously. A useless test would fall along the diagonal. The AUC summarizes the whole curve in one number. An AUC of 0.92 means that if you randomly picked one diseased and one healthy animal, the test would correctly rank the diseased animal higher 92% of the time. When choosing a cut point, the optimal point is geometrically the one closest to the top left corner, but in practice, you may deliberately shift it. If missing disease is catastrophic, shift toward higher sensitivity, even at the cost of specificity. If false positives are costly or harmful, shift toward higher specificity. Likelihood ratios are the most clinically flexible diagnostic metric, and they're underused in veterinary medicine. Here's the key advantage. Unlike PPV and NPV, likelihood ratios don't change with prevalence. They're a property of the test itself, like sensitivity and specificity, but they're expressed in a way that directly tells you how much the test result shifts your clinical probability. LR plus of 12.7 means a positive result makes disease about 12 times more likely than before you ran the test. LR negative of 0.12 means a negative result makes disease about 8 times less likely. You can combine these with your pre-test probability, your clinical estimate before the test, to get a post-test probability. This is the Bayesian approach to diagnostic reasoning, and it's exactly how experienced clinicians think, even if they don't use the formal terminology. The practical rule, LR above 10 or LR below 0.1 are the ones worth getting excited about. Between 2 and 5 or 0.2 and 0.5, the test is shifting your probability, but not dramatically. Work through this case question together. First, the study population. Prevalence 35%, sensitivity 82%, specificity 88%. Using the 2x2 approach with 310 cats, approximately 108 have HCM, 202 don't. True positives equal 0.82 times 108 equals 89. False negatives equal 19. False positives equal 0.12 times 202 equal 24. True negatives equal 178. Positive predictive value equals 89 divided by 89 plus 24 equals 79%. Negative predictive value equals 178 divided by 178 plus 19 equals 90%. In the study population, a positive result has a 79% chance of being a true positive. A negative result has a 90% chance of being a true negative. Reasonable performance. Now your general practice, 8% prevalence. With 310 cats, 25 have HCM, 285 don't. True positives equal 0.82 times 25 equals 21. False positives equal 0.12 times 285 equals 34. Positive predictive value equals 21 divided by 21 plus 34 equals 38%. In your practice, a positive NT-proBNP result is only correct 38% of the time. More than half of positive results are false alarms. That's a very different clinical picture. Would you use it to rule in or rule out? With sensitivity of 82% and LR negative equals 1 minus 0.82 divided by 0.88 equals 0.2, a negative result meaningfully reduces the probability of HCM. This is better as a rule-out test in a low prevalence population. A positive result in your practice needs confirmation. Echocardiography remains the gold standard. Key lesson: always recalibrate published PPV and negative PP, published positive predictive value and negative predictive value to your own practice prevalence before applying them clinically. To sum it up, diagnostic test accuracy is one of the most practically important areas of veterinary literature interpretation. The 2x2 table gives you everything you need. Sensitivity and specificity describe the test. Positive predictive value and negative predictive value describe performance in a specific population, and they shift with prevalence. ROC curves let you compare tests and choose cut points. Likelihood ratios let you apply test results to any pretest probability regardless of the study population's prevalence. The single most important habit: always ask what the disease prevalence was in the study and how that compares to your own clinical setting. That one question will save you from misapplying test results more than any other. If you'd like more short, clear epidemiology lessons, go ahead and subscribe before you head out. And if this video helped, a quick like tells YouTube to share it with other students who might need it. See you next time.